Okay, folks, let's get started. So it will become clear today why I have been torturing you with all those strange things called commutators so far. That is because we will now look at a formalism that is, on the one hand, is quantum mechanical and quite powerful, but on the other reduces to simple diagrams, which you can teach to chemists and biologists without the necessity of introducing the colossal amount of background physics that they might not necessarily be familiar with. So, but I will first derive it using serious physics, and then we will derive those diagrams, and then I will teach you how to use them. So I will remind you that the observable, so if we have an operator O as a function of time in the density operator formalism, is the trace of the corresponding operator O multiplied by the density matrix that is a function of time. And it follows the von Neumann's equation. Now, if we are to ask ourselves, well, we might not necessarily want to go through the deep, dark quantum mechanics of the density matrix, but what we are certainly interested in is how the various observables move as functions of time. And why don't we try deriving equations of motion for the observables themselves? So, what I'll do is I'll take a derivative. So d by dt of this O of t is going to be, so the derivative of this trace, d by dt of trace of O is rho of t. Now remember that trace is a linear operation, it's just a diagonal sum across the matrix, so we can pull the derivative inside. O is a constant operator, this is our observable, we can take it out of the derivative, and so we are left with just the derivative of the density matrix. So, trace of O d rho dt. Okay, but of course we know what d rho by dt is from von Neumann's equation, so why don't we substitute that there? So it will be a trace of O times minus I H commutator with rho. So what I simply did here was to replace the derivative with the right-hand side of the von Neumann's equation. Okay, so I will take I out of the bracket, I will open up the commutator, so what we are going to have is minus I trace of O, then it's H rho, so H rho minus O, and then rho H. Okay, so that is everything opened up. And what I will now do is I will use the other property of the trace. Remember, I mentioned it briefly. Trace ABC is equal to the trace of these matrices that have been permuted cyclically. So you can do cyclic argument permutations and products under traces. So CAB, for example. So we can rotate C over to that side. Okay, so I will now do that here. So I will shift H over there and see what's going to happen. So that is minus I and then trace of O H rho and then minus, so H over here, H O rho. And then, look, I can take rho out of the bracket. So that is minus I. And what I will also, oh yeah, let's take it out of the bracket and take it. So that's trace of, and then we have O H minus H O times rho. And we can recognize a commutator here. What I'll do is I'll swap this commutator around and I'll remove this minus to make it a commutator HO. So what we have is I trace of the commutator H with O 0. And see what we've arrived at. This is actually the observable, right? Remember the definition of an observable. It's an operator traced with the density matrix. And so that's the observable corresponding to this commutator. So this is I observable H. And so we arrive at a very important equation in spin dynamics. It says that d by dt of some observable O is I times the observable of H with O, where H is the Hamiltonian. And notice that the density matrix is gone from this equation. And also notice that at least for simple cases, we know all of these commutators because we've been calculating them through half of this course so far. So, what I will now do is I will start using this to derive, for example, Bloch equations. So why don't we start with deriving the equations of motion for Lx, Ly, Lz, spin operators, under just the standard Zeeman Hamiltonian. So if we have our H, that's equal to omega Lz. So we have the magnetic field on the z-axis. And now that we know the Hamiltonian and we know the operators, we can actually find out those equations of motion using this. And if we now obtain Bloch equations using that, then probably everything is working. Okay, so let us do that. So we would have d by dt of, starting with Lx. That would be I, and then I would take omega out of the bracket, so I omega, and then we have the observable of Lz with Lx. Because our Hamiltonian is omega Lz and our observable here is Lx. However, we do actually know what the commutator of Lz and Lx is. It is I Ly. And so the result is I and I give us a minus, that is omega Ly. And that is really quite nice, right? Because that actually is the first Bloch's equation in the absence of relaxation. Okay, then d by dt Ly is going to be I omega, and then our commutator is omega Lz, and here the observable is Ly. And the observable of Lz with Ly, look, as cyclic permutations go, this is the wrong way around, so this is minus Lx. Minus I times I is a plus, and so we have plus omega Lx. And finally, Lz commutes with itself, so the commutator is 0, so we have d by dt of Lz is 0. And so when we notice that our magnetic moment is proportional to the three projections of the spin here, we do get those equations. So I will rewrite these ones, and what I will also do is I will introduce this notation. So Lx without the hat will be the expectation value of the corresponding operator. So if this doesn't have a hat, then that's simply the observable, right? So a scalar, not a matrix. Okay, so what we get from here, Z we don't need to worry about. Our magnet is along Z, but the XY dynamics we're interested in. So the conclusion from here is that d Lx by dt is minus omega Ly, and d Ly by dt is omega Lx. And remember, we solved this actually a few lectures ago, but I will remind you again what the solutions are here. So what I will do is I will differentiate the first equation again. So what will happen is d2 Lx by dt squared will be minus omega dLx by dt. And what dLx by dy by dt? And what dy by dt is, we know from the second equation. It's omega Lx. So that is therefore minus omega squared Lx. And that is the second order ordinary differential equation. dLx by dt squared is minus omega Lx. In your mathematics course, you remember what the solutions have been. They're cosines and sines. So we have Lx, therefore is equal to a cosine omega t plus b sine omega t, where a and b are indeterminate constants that depend on the initial conditions, and omega is this frequency. And you can check this solution by direct inspection. If you just differentiate the cosine twice, minus omega square will pop up in front, and you get the cosine back, and likewise with the sine. Okay, so this is our Lx, and then Ly is omega dLx by dt, and so we can get Ly out of there as well. Okay, so we have Ly, so let me rewrite Lx here. Lx is a cos omega t plus b sine omega t, and then Ly from here we conclude that Ly is 1 over omega dLx by dt, and therefore this is going to be Ly equals, so the cos would give us a minus sine, minus a sine omega t, and then sine would give us plus the cos, plus b cos omega t. And these are the general solutions for that. And if we specify some initial condition, for example, Lx at time 0 would be 1/2, and Ly at time 0 would be 0. So the standard initial condition when the magnetization starts on the x-axis. Then we would have here b is going to be equal to 0, and a is going to be equal to 1/2. So we would have Lx is 1/2 cosine omega t, and Ly is 1/2 is a minus, because it's counterclockwise dynamics, sine omega t. Okay, so these are our solutions, and you can see it's the usual precision. So what this allows us to do is to formulate simple diagrammatic rules for how we deal with that magnetization. So what we just did was to have our evolution generator, the Hamiltonian here, being equal to omega Lz. So we write it here in the center and draw a circle around. And what was happening under it, if you look at how the evolution unfolded, we had Lx, and that Lx was rotating through the cosine and sine relationship into Ly. Right? So we would have Ly here, and then there's a rotation. And then Ly would further rotate into minus Lx, and Lx would further rotate into minus Ly, and then finally back here. Now, of course, the labels are all allowing cyclic permutations, so none of this mathematics will change if we replace x by y, y by z, and z by x. And so we have two corresponding diagrams for the x and the y. So under omega Lx, we would correspondingly have, if we start our dynamics in Ly and go through the mathematics, we would notice that Ly would rotate into Lz, and then onwards to minus Ly, and then onwards to minus Lz, and then back into Ly. And then finally, under omega Ly, we would have Lx. So starting with Lx here, going into minus Lz, and then going into minus Lx, and then back into plus Lz, and onwards to Lx. So these diagrams are convenient also because they don't just apply to an individual spin, they apply to multi-spin systems. Imagine we've got some product state. So for example, Lx Sx. Remember what that was? It was the observable corresponding to Lx Kronecker product Sx, right? Where those are individual spin operators of the two spins. But remember what I told you about the properties of such direct products. If we have a Kronecker D times C Kronecker D, that is the same as AC Kronecker BD, when all the matrices have the same dimension. And so A acts on C and B acts on D. So in these direct product relationships, each individual operator only acts on its corresponding operator. And so under all of these dynamics, if we are acting on this with only just, so let's say we have Lx Sx, and we are acting on it with only the L operator, so for example Lz, then what is going to happen is, if we look at this diagram, Lx is here, so we have Lx Sx cosine omega t, and then we have plus Ly sine omega t. So nice, simple, Ly Sx of course. So Lx rotates into a combination of x and y, but Sx just lives on because nothing acts on it. And so it is possible, therefore, to use these rules not just for single operators, but also for product operators. And so collectively, these rules are therefore called product operator formalism. Right? And so for the single spin rules, we have just derived them. Okay, so now what these rotation diagrams correspond to, trigonometrically, is just very simple things. We have Lx going under omega Lz into Lx cosine omega t plus Ly sine omega t. So that was the diagram here, so rotating in that direction. If we have Ly under omega Lz, that would likewise be this. So we have Ly cos minus Lx sine. So Ly cos omega t minus Lx sine omega t, and Lz remains unchanged. Because it commutes with the evolution generator. So these are the trigonometric rules which these diagrams encode. And if you look into your handout, you've got those diagrams listed on the very first page. And they more or less describe any pulse sequence that deals with the dynamics of a single spin. So in the next lecture, we will, for example, look at the product operator treatment of spin echo, and we will see that these diagrams suffice. And so you can see that on the one hand, we have rather horrendous quantum mechanics that one would have had to go through if we were to describe this quantum mechanically. On the other hand, we haven't actually made any approximations or assumptions anywhere here. And so these diagrams, rotation diagrams, which you can easily explain to the biologists, are actually exact. And so this is why a lot of textbooks, they don't even mention quantum mechanics, particularly in MRI, where the audience demands, but go straight into these trigonometric relations and still give people tools to analyze their pulse sequences quite rapidly, as you can see, because they will simply be trigonometric transformations. Okay, but to us, these transformations are actually quantum mechanical propagation laws. So I will rewrite, for example, the first equation there. Remember what happened when we solved Liouville van Neumann's equation. So if we had Lx operator, that was our initial density matrix. Then we had two matrix exponentials on either side. It was e to the minus I omega Lz t, and then e plus I omega Lz t. And if you work through all of the commutators that this entails, you will get exactly the same relation, but with the operator. Of course, it will be Lx cosine omega t plus Oy sine omega t. So this is something that mathematicians call isospectral flow. So it's an action by a real algebra on itself. And of course, this is all terribly quantum mechanical and matrix values and so on, but those diagrams provide a serviceable substitute.